Let us say we want to implement this equation y is equal to square root of a square plus b square. Now implementation of this equation will require one multiplier for calculating a square, one multiplier for calculating b square, one adder to add them, and one block which will calculate the square root of a number. An algorithm named Cordic can calculate the square root of a number. Xilinx provides Cordic IP which can calculate the square root of a number. The problem with that IP is it consumes 47% of the 1200 series FPGA, which is a substantially large chip used in many imaging applications. Now, if only one block of the design is consuming 47% of the chip, then it is not a good sign. Moreover, it will consume the corresponding power dissipation in the chip. Now, let us consider a scenario where a little error is acceptable in y. Okay, that means we don't want the exact value of y, but the value of y should be closer to the square root of the sum. There is an existing equation called as alpha max plus beta min algorithm. The equation is like this: alpha max plus beta min. So what it does is it finds the maximum number among a and b, that is multiplied by alpha. It's a fixed number, it's a coefficient. Then it finds the minimum number among a and b, that is multiplied by beta. Again, it is a coefficient. The value of alpha is 0.93 and value of beta is 0.4. Now, if we implement this equation to find y, it requires one multiplier here, one multiplier here, plus it requires one adder. So it requires same number of components other than Cordic. So if we implement this equation, we do not need a Cordic block. Now in one of my work, I needed this equation, y is equal to square root of a square plus b square, but a little error in this number was acceptable. So I implemented this equation. Now I didn't stop here, I went ahead and I modified this equation. I wanted to modify the equation so that the resources of the equation can be further reduced. So what I did is, I modified this 0.4 to 0.5. Okay. Now, when we are working with FPGA, all these numbers will be in binary. Alpha will be in binary, max will be in binary, beta will be in binary, minimum will be in binary, and again the y will be generated in binary. So we are dealing with binary numbers. Now what is the advantage of having 0.5 here? That is the question. The answer is 0.5 is a special number in binary. Why is it a special number? We will see. If we want to understand any number system, first we need to understand the decimal number system properly, which we use daily. For example, let us say we want to multiply a number 56 by 10. What is the answer? The answer is 560. We can tell it quickly. Okay. Now let us say we want to divide 560 by 10. What is the answer? Answer is 56. This we can tell quickly because we know if you want to multiply a number by 10, we just have to add one zero on the right hand side of the number. Similarly, if you want to divide a number by 10, you have to just discard one digit on the right hand side. Now, let us put it in a statement. What is the base of this number system? 10. Now there is a similarity here. So how do we define it? If you want to multiply a number by the base of the number system, you just have to add one zero on the right hand side of the number. Right? Similarly, if you want to divide a number by the base of the number system, you have to discard one digit from the right hand side. Now this is applicable to all the number systems. Let us consider a number in binary 1 1, which is equivalent to 3 in decimal. If you want to multiply this number by its base, which is 1 0, which is 2 in decimal, it's equal to 1 1 0. Now this is equivalent to 6 in binary, right? Let's say we want to divide this number by 2, which is the base of the number system. It's again 1 1, which is equivalent to 3 in decimal, right? Now if you want to multiply a number by 0.5, that is, if you want to divide a number by 2, you just have to discard one bit from this number. Now again, if you want to implement this equation on a processor, you will have to use one shifter. But if you want to implement it in FPGA, you will not need any component. You will just have to discard one bit. So if you want to multiply 0.5 and mean, you will not need any component. So this one multiplier will be saved. So now the total number of component required is one multiplier here and one adder here. So we have reduced one multiplier from the approximated equation also. But there is one thing that we have to remember. What is that thing? That we have unbalanced the equation by modifying one of the coefficient. Now if we want to maintain the equation, we have to balance this coefficient also. So after some statistical analysis, I found out that if you want to move from 0.4 to 0.5 for beta, for alpha you have to move from 0.93 to 0.9375. Okay. If you implement this, the maximum percentage error is 9. Okay.